11.0 is talking about sample spaces and the fundamental counting principle. And they start off in this first problem. It says, represent the sample space using set notation. So you need to know what a sample space is. And it's not hard. It's just, what are we talking about in this problem? Or how many choices are in this problem? So sample space, a hot dog stand offers both small and large hot dogs. So the sample space, notice it says use set notation. Set notation is just like squiggle brackets, okay? Not parentheses, but squiggle brackets. It indicates that there's a list coming, all right? And basically, we only have two choices. Either we have small or we have large. And you could say small hot dogs and large hot dogs if you want, but basically that's it. That's the sample space. And what's important about that is just to notice that there are two things, okay? That's sample space. So when we look at number 3, it says a new car is available in red, white, green, and black, all right? So the sample space is going to be a list of, let's abbreviate this, R for red, W for white, G for green, B for black. All right. All we're trying to do is just list out what's possible in the problem. This chapter is going to have some pretty difficult problems, and one of your first steps is going to be just to identify what is possible in the problem, or how many things are possible in the problem. I see 4 different elements in this sample space. So then you look at number 5. A room in a house needs to be painted. The room can be painted white, yellow, or pink. So the sample space is going to have white, yellow, or pink. Now you feel free to write out the whole word, white, yellow, pink, but that's the sample space for this problem. All right, now the next problem set is a little bit harder because now we're finding the number of possible outcomes in the sample space. Okay, so number of possible outcomes is what we're trying to find. So 5 books need to be placed on a shelf. You randomly arrange the books on the shelf from left to right. Now, this is a lot harder. Okay, the only number that you have is 5. But basically, the fundamental counting principle, all right, this is fundamental counting principle. And I like to refer to fundamental counting principle as a blanks problem. Blanks problem. Yeah, fill in the blanks. All right, so fundamental counting principle is a blanks problem. When I see this problem, 5 books need to be placed on a shelf. You randomly arrange the books on the shelf from left to right. So in my eye, I see 1, 2, 3, 4, 5 blanks. And we're going to fill in books into these 5 spaces. All right. Now, fundamental counting principle is basically us asking the question of how many ways are there to do whatever they're talking about in this problem. All right. So when I look at this problem and I'm trying to decide how to arrange these books on a shelf, I need to think about how many ways are there of filling in this first space on the shelf. There are 5. Okay. So you've got 5 different books. You can pick one of those 5 different books. All right. Now you pick one of those books and you put it on the shelf, and now you've got another blank. How many ways are there to fill in this? 4. Very good. And then the next one, there are 3 books left. And then the next one, 2. And then the last one, there's only 1 choice. You've got to do this. Now, the blanks problem also, by the way, you are multiplying 5 times 4 times 3 times 2 times 1 is going to be the answer. All right. Now, that's something special called a factorial. 5 exclamation point. But when we do 5 times 4 times 3 times 2 times 1, that's 120. So that is the answer, 120. But That's what a factorial is. So if you find that factorial button, it's an exclamation point on your calculator. That does 5 times 4 times 3 times 2 times 1. 5 factorial. All right, so let's look at number 8. The chess club must decide when and where to meet for practice. The possible days are Tuesday, Wednesday, or Thursday. The possible times are 3, 4, or 5 p.m. There are 8 classrooms available. All right, so fundamental counting principle is a blanks problem. And basically you have to decide 3 things. You have to decide a day and a time and a classroom. Those are your 3 decisions to make. Those are the 3 numbers in the problem. And those are the 3 blanks in the fundamental counting principle. All right, so all that it's going to take here is to say how many days are possible in this problem? 3. And how many times are possible? 3. And 8 classrooms. We need to multiply those 3 numbers together. 3 times 3 times 8 is 72. There are 72 ways of doing this situation, all right? So when we are counting, in this chapter, when we are counting, we're answering the question of how many ways are there of doing such and such. 6 books need to be placed on a shelf. You randomly arrange the books on the shelf from left to right. Well, this is the same question we just saw, right? This is going to be what? Right, 6 factorial. Or 6 times 5 times 4 times 3 times 2 times 1. $720. Okay. A padlock's combination is 5 digits long. A padlock's combination is 5 digits long. Okay, I guess the key here is digits. This was a tricky question for me because like you wouldn't think of like a master lock. Like when you've got like a master lock, that's thanks. Usually there's like 40 numbers here and you got all the way around or something like that. But that's not what this is, okay? That's not what this is. This reminds me more of like a luggage lock. I don't know if you've ever put a lock on a luggage. Basically, there's like 1, 0, 9, 4, 7, 2. Okay, they're talking about digits. So a bike lock, yeah, that's a good idea. So you got to turn these digits. Yeah, you spin the digits around. And digits means there's 10 choices. Okay. So it's not a like a I don't know that I think of this as a padlock. But anyway, they say there are 5 digits long, so that means there's 1, 2, 3, 4, 5 blanks. How many choices in each blank? What's the difference between 10? Why is this 10, 10, 10, 10, 10? The question is, can I use the same number twice? Sometimes a problem will say you can't use the same number twice. They'll say no repeats. But this one, there's no reason why we can't use the same number. I could be 5, 5, 5, 5, 5 if I wanted to, or 7, 7, 7, 7, 7. All right, so shortcut to typing this in, that's 10 to the 5th power. 10 to the 5th power, 100,000. Yeah, sure. There you go. I'm all about shortcuts. Number 11. When a button is pressed, a computer program outputs a random odd number greater than 1 and less than 11. Greater than 1 and less than 11. You press the button 4 times. Okay, odd number. All right. I think it's useful to identify the sample space in this problem. Okay. So let's just list out the numbers that they're talking about. Odd number greater than 1, less than 11. What's the first odd number in this list? It's got to be greater than 1. Yes, right. It's useful for me to list out the sample space in this problem because otherwise it's kind of hard to tell how many choices there are. You press the button 4 times, so 1, 2, 3, 4 blanks, and you know how many numbers could go in the blank? 4. And then am I allowed to have the same number again? So how many in the second blank? We've got 4 to the 4th power. 4 to the 4th power is 256. Sometimes the wording on these problems is really tricky, and so you have to read carefully and really, really think about what it says. 5 rooms in a house need to be painted. Each room can be painted white, yellow, or pink. Okay? 5 rooms in a house. So room number 1 and room number 2 and room number 3 and room number 4 and room number 5. How many choices to paint that first room? 3 colors, right? And 3 colors and 3 colors and 3 colors and 3 colors. That's 3 to the 5th power. 243. I like these problems. I think they're kind of interesting, kind of fun, and kind of quick. Number 13, you flip a coin 8 times. All right. So think about the sample space. What could potentially happen in this problem? Heads or tails? I don't believe that. Okay. Well, we're going to assume that you can only land on heads or tails. All right. That's true, I suppose. But if we made that third possibility of landing on its side, then I don't know what the probabilities would be. It would be a much, much more difficult problem. Anyway, flip a coin 8 times means 1, 2, 3, 4, 5, 6, 7, 8 blanks. How many choices for each of those blanks? Is that 2 to the 8th power or 8 to the 2nd power? Either one? Mm-mm. That's 2 to the 8th power. 2 to the 8th power is 256. Not the same thing as 8 to the 2nd power. A spinner can land on either red or blue. You spin 7 times and then roll a 6-sided die. Ooh. Okay. So everybody know what they mean by a spinner? You got a game board and you flick this little arrow and it spins around and around and around and around. But it's either going to land on red or blue. So there's only 2 choices here. So spin it 7 times and then roll a 6-sided die. So a 6-sided die is going to have 6 possible outcomes. Okay. So I've got 2 to the 7th times 6. 2 to the 7th times 6. 768. Is that right? 2 to the 7th times 6. Of course, you could do 2 times 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 6 as well. 15. Spinner can land on either red or blue. You spin 7 times. So that's just 2 to the 7th. We just did that. 2 to the 7th is 128. Okay, last one. A football player attempts 6 passes in overtime. Each pass attempt results in a completion, an incompletion, or a turnover. So the sample space is completion, incompletion, or turnover. There's 3. 6 times. Right. So not 3 times 6. 3 to the 6th. 3 to the 6th power. Very good. 729.